Yeah, good. Now, you notice this thing here, the formula for variance, was quite long, wasn't it? It's quite long. It took quite a long time to do, okay? So what we can do is find a little bit of a shortcut and use the one which I prefer using, okay? So we know that the expectation of x is equal to x times p. So let me write this down. So sum of x times p is the expectation, okay? Now, let's think about this. What do you think the expectation of something squared is going to be? So you take your random variable, each of these outcomes, and instead of using the outcomes they are, what happens if we square it? What do you think that's going to be equal to? So the expectation of x is the sum of x times p. What's the expectation of x squared? Perfect. Well, not quite. Not quite. Okay? Because have a think. All we're literally changing here is the x. So x and x. Now we're changing that to x squared. Doesn't make sense just to change that instead. Yeah? It's like saying the expectation of y is going to be the sum of y times p. The expectation of z is going to be the sum of z times p. Is that fair enough? Okay. So let's have a think then. Let's have a think. Would you be happy that this thing looks a bit like this thing or this thing? Yeah? Would you be happy with that? So this thing over here, sum of this thing times p, looks a bit like an expectation. Yeah? In fact, it looks a bit like the expectation of what? Happy with that? Because logically that should be the sum of this thing. You happy with that? It's a similar kind of idea. Similar kind of idea. Does that make sense? Yeah, so I'm just literally looking at that, and intuitively it makes sense. I'm not going to give you a proof for it, but intuitively it makes sense, and in fact it is absolutely true. Okay? So let's have a think then. Let's have a think. I have said that the variance of x should be equal to this. Okay? So the variance of x should be equal to this. So the variance of x, because the variance of x is equal to that, that should look like the expectation of x minus mu, do we have capital, all squared. Happy with that? Because the variance of x is literally given by this formula, and I've said that that looks like the expectation of x minus mu all squared. So far, so good? Okay. Now, what happens if I expand this thing out? So I'm going to use square brackets. What's x minus mu all squared? If I was going to expand that out, what do I get? Good, absolutely. Yeah, it's just quadratic, okay? Now, I'm not going to give you the proof for this yet. It will come, okay? But actually, if I take the expectation of three individual things, which I'm adding together, or subtracting in this case, that should be exactly the same as the expectation of x squared. In fact, this should be a capital. Okay? This should be exactly the same as the expectation of the first term minus the expectation of this term plus the expectation of mu squared. Make sense? Yeah, makes sense? Good, okay. So this is where we're at the moment. Okay. So have a think then, have a think. We can simplify this ever so slightly. Okay? What would the expectation of mu squared be? Remember mu is just a constant. Mu is just your number. Okay? If you square this, it's still a number. So what's the expectation of a number? What value do you expect to get of 3? What's the expectation of 4? What's the expectation of 5? It should just be that constant. Yeah, it should just be mu squared. Does that make sense? Right? So we've got now, let's do it over here. So I'm saying the expectation, so the variance of x, I'm just going to continue up there, should be equal to the expectation of x squared minus the expectation of 2x mu plus mu squared. Make sense? Good, fantastic. Okay. Now, let's have a think. Would you be happy that in this case, the 2 and the mu are both constants? Make sense? Yeah? So the 2 is a constant and the mu is a constant. So surely the expectation of 2 mu should just be a constant. So therefore, this is going to be the expectation of x squared minus 2 mu, lots of the expectation of x plus mu squared. So far, so good? So far, so good? No? Why not? These are just numbers, okay? So it's just like the expectation of 3x should just be 3 lots of the expectation of x. Or the expectation of 5x should be 5 lots of the expectation of x. They're just numbers, because 2 is a constant and mu is a constant as well. It's just a number, okay? So let's have a think about this then. Let's have a think. Would you be happy that mu and mu are really just the expectation of x? Yeah, so I could rewrite this then as the expectation of x squared minus 2 lots. Well, this is going to be the expectation of x, that's what that mu corresponds to, times by the expectation of x plus the expectation of x all squared. That makes sense? Okay. And are you happy that if I'm timesing the expectation of x by itself, that should just be the expectation of x squared? Like so, plus the expectation of x squared. And would you be happy if I'm taking away 2 of something and adding one thing later on, what do I get? Sorry, that's the squared. So that then is a new formula for variance, which might be slightly quicker. That might be slightly quicker. Okay, where this thing, the expectation of x squared, this thing here, is just the sum of x squared times by p. Yeah, and we know what expectation of x is. It's just the sum of x times p. Is that okay? Now, good news for you is that in the formula book, you get both of those formulas. You get both this one, and you also get this one as well. Okay? So it's up to you which one you use. I would advise thinking about this one, because it's much quicker. Okay? But if you wanted to use the other one, you're fine to do that as well. In fact, this one will come in handy later on anyway, so I'd advise you to get familiar with that. So the expectation of x squared minus the expectation of x all squared should just be the variance. All good?
Lots of changing the...
Good news for you is the only formulas you need to know, if I get rid of that bit, the only formulas you need to know are this one, so the expectation, and the variance. So you can either use sum of x minus mu all squared times p, or you can use our newfound formula, which is the x squared minus e of x all squared. Okay? So if you didn't follow any of that, all you need to know is the result. Okay? But obviously I'm a mathematician. I don't just tell you results, I show you where the results come from, because it's all linked together. And actually, if you can try and follow that kind of thought process, then you're going to make yourself a stronger mathematician anyway, because then eventually you'll be able to do it yourself. Is that all good? Any questions?
So this is an introduction to expectation, where we have to use this formula when we don't have the sample, so this is how we...
Absolutely right. Yeah, so if I give you a probability distribution, in other words, I give you a set of outcomes and I tell you how to work out their probabilities, okay, then in order to work out expectation, mean, or variance, you would need to use one of these two formulas. Yeah? because you no longer have that sample size there. Whereas if I actually give you a set of data and say, go and find that standard deviation, go and find that mean, you should now be able to do that as well. Okay? So what I talked through today was the idea of a probability distribution. The idea of saying, here are a set of outcomes and here are their associated probabilities, or how to find their associated probabilities. So if I now ask you to find the expectation, you should be able to do that. And if I ask you to find the variance, you should also be able to do that.